to make this problem sort of well posed, let's assume point contact. So what we're assuming is that it's an infinitely rigid ball in an infinitely rigid bowling alley, and they only touch at a point here. And let's assume let's assume no air friction, or let's neglect air friction. And the question is, if we look at the angular momentum relative to this point C, and let's take our angular momentum to be positive in this counterclockwise direction, is it, after the ball ends up rolling, is the angular momentum bigger at 1 than it is at 0? Is it less? Is it equal? Does it depend on the coefficient of friction? Or is there something ill-posed about the problem, something else going on? And you have a couple minutes to work on it, and you can talk to each other about it. Any questions for me about the question? Questions for me about the question? Okay. Could everybody vote A just for the moment? Just everybody vote A, just so I can see how many people are in the room. Everybody vote A. More people vote A. Okay. Okay, we're starting the vote all over again. If you voted, you have to vote again. Question, yes.
Are you asking which end is the magnitude?
Okay. What does it mean for a vector to be bigger than another vector? It means that the magnitude of the vector is bigger. If you like, that's true. Other questions? Okay, 10 seconds more. 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, 10. We lock it up. We look at how you voted. Okay. So let's try and work this out. So we start out by drawing a free body diagram. So we draw a free body diagram of this thing. We've got mg like this. We have n like this. And we have a friction force like this. And that looks like a pretty complete free body diagram. When it's sliding, during sliding, we know that F is equal to mu n, and otherwise, in the rolling part, for example, we know that F is less than or equal to mu n. Okay, there we've got that. Now we've got this point C over here, and we could have some coordinate system, let's say I and j like this, and we could name some points here. Let's see, here's a point G, here's a point, let me call this point D. And there's a dotted line, a horizontal dotted line like so. And we can start out with a linear momentum balance equation. Linear momentum balance says that the sum of all the forces on this thing is mass times the acceleration. Note that in what I call the linear momentum balance equation, we don't see linear momentum at all. We see the rate of change of linear momentum. So that's a funny thing in my vocabulary. I learned it in graduate school, so I think I'm not the only one who uses it. But linear momentum balance has to do with the rate of change of linear momentum, most often. What do we have here? We have an n minus mgj, and we have a plus fi equals the mass times the acceleration, and this is the acceleration of this point g. And if we assume that this thing doesn't jump off the ground or fall through the ground, we know that that point g stays constant distance above the ground, so it's only got an acceleration in the x direction. If we take this equation and dot it with j, we get the intuitively obvious result that n is equal to mg. It's not accelerating up or down, so the bowling alley is holding the weight of the ball whether it's spinning or not. Okay, now we know n is equal to mg. Now, what if we look at angular momentum balance? And we're going to look at angular momentum balance relative to c. And what does that say? It says that the sum of the moments relative to c is the rate of change of angular momentum relative to c. And here we have angular momentum balance, and the quantity angular momentum doesn't show up here. It's the rate of change of angular momentum. Any equation where you're equating something about forces to something about acceleration, mass times acceleration, you call linear momentum balance, whether you're using the acceleration version or the velocity version. Anything where you're talking about torques and angular momentum, we call angular momentum balance, even if we're over here in the derivative world, which is actually the more fundamental world. Okay, now we need to figure out what are the moments of all of these forces. Well, think about it for a few seconds. Okay, we just had an example of something very important. Yes?
Can I ask a question?
Yes.
How do you know the forces to the right?
Say again?
How do you know the friction forces to the right?
I don't necessarily know it, but for things that I assumed about this problem, which is that this had zero initial velocity, angular velocity, and it had a velocity to the left, so this is sliding this direction. And the assumption we make about friction is that the friction force resists relative motion. So it is true, to figure out the friction force, you have to know the direction of the sliding. Okay, now what was the great thing that was just illustrated was something about modern architecture. You were all totally quiet. We've got this room that has this ambient noise, like this fan over here. Maybe there's some ventilation noise. In the old days, we used to have rooms without this electrical noise, and when a room was quiet, it was really quiet. Like this quiet we have here, just doesn't cut it compared to that. You know what they call it, in the old books they say you could hear a pin drop. You couldn't hear a pin drop anymore because we have all this ambient noise. Anyway, those were the good old days. In this room too, they didn't have the carpet in here too, so it was echoey. It was really nice. Okay, but that was pretty nice. Now, I'm going to ask you a question, so get ready for it, and then I want you all to answer out loud. This thing for this problem is? 0. Very good. So 0 is equal to h dot relative to c. Therefore, h relative to c is equal to a constant, or a constant vector. Therefore, h relative to c1 is equal to h relative to c0. Okay. Any questions about that? Any questions about it? Yes?
So, I guess, doesn't it slow down a bit?
Okay, so doesn't it slow down? And that question has a few aspects to it. So my game here is how much better than can I do than 20%, right? So my goal is to do better than random and to put. Okay, that's not my only goal. How many people don't like it that I make the questions tricky like this? Find it annoying? Okay, but it's not. I know they're tricky, and I try to make them tricky before I explain it. Presumably, after I explain it, we get the scores high again, like the last class when I gave the same question again. Okay, so let's talk about this question. Doesn't it slow down? So, in this sliding phase here, this force here is not 0, and so mass times acceleration is equal to this force. It's got an acceleration that direction, and had a velocity that direction, so the velocity decreases. So yes, the speed slows down as it slides along the bowling alley. Yes?
Yes, I get it.
Okay, but there is a related question. What happens after it starts to roll? After it starts to roll, then we don't know what this force is, but we know that this thing is rolling along. Now, does it roll faster, slower? How does it roll as it rolls along? Does it slow down or not? Okay, why don't I just leave that as a puzzle problem? And you can think about whether when you roll a ball, it slows down or not, even with no air friction. You have a question?
Can I pick up that phone?
So the disadvantages of security on your telephone is that we could not call your friends and tell them to tell you that we had your telephone because I couldn't read your Chinese password to. Okay, so you can puzzle over this problem. Let's go. So, question is: does a rolling thing slow down or not, even without air friction? If in your experience it does slow down, the question is why does it slow down, and how does this show up in this picture? So let's go on to talk about collisions. In some sense, collisions are easier than equations of motion because we don't have to solve differential equations. But sometimes it's just a slightly different skill. Let me motivate this with a video. So this is I'm going to show you a robot from my lab. It's actually a robot we copied from somebody else, and it's the robot that got me interested in robotics. So this is the machine. This is a copy of the machine that got me interested in robots to start with. And this thing just walks downhill. So people ask how my research is going. I say it's all going downhill. Haha, exactly. Okay, so this is just sticks and hinges. What is this thing doing? It's obeying the equations of dynamics that we're learning in this class. You can't quite, at this point in this class, probably write all the equations for this because it's just a little too complicated. In principle, you could, but it's just a matter of getting organized because there's several parts here interacting. And the one thing that we haven't done, which is I'm going to do today, is talk about collisions. We believe, we meaning me and some other people, that this actually catches some of the essence of human walking, certainly looks something like human walking. And not only that, but that this issue of having differential equations interacting with collisions. So when your foot hits the ground, it's a collision. This thing, if we had the sound on, you hear it go bang. When your foot hits the ground, it hits kind of quietly. But we believe that what happens when you put your foot down when you walk is much the same thing as what happens here, which is that you slow down, that energy is lost when that foot hits the ground. Then we have this more or less conservative energy conserving system, which is not true for human walking because there's muscles involved. Here, energy is being supplied by gravity because it's walking downhill, and then energy is lost again here. So in real walking, sort of an interesting thing, by the way, is that backwards walking looks almost like forwards walking. In real walking, there's an energy balance, which is that the muscle work is balanced by the energy lost in this collision, whereas here it's gravitational potential energy that's made up by, that makes up the energy lost in the sequence of collisions. Okay, so we'd like to understand a little bit about how collisions work, and that's what I was going to talk about now. Any questions, quick questions about this video? Yes?
Can the robot not walk on flat ground?
That robot cannot walk on flat ground because energy is lost every time the foot hits the ground, and on flat ground there's no way for the energy to be made up.
But doesn't it have some kind of motor or something?
This has no motor in it.
Wait,
Is that a robot?
why is it moving?
Like mechanical device?
This is a semantic question, not a dynamics question. We call it a robot. You can call it whatever you want. What?
Is there nothing powered on it?
That's correct. Those are pieces of metal which are connected with hinges.
Okay.
There's no motors, there's no computers, there's no nerves, there's no muscles. You can't see the string connected to the ceiling which is holding it up because it's not there. Yes? You can see it a little bit by just keeping track of this height here and this height here. And this is probably something like 2 or 3 degrees. Does it matter exactly? So when we do computer simulations of this, less than a certain slope it won't walk, more than a certain slope it won't walk. In the lab we sort of pick a slope where it seems like it works pretty well. We have designs which on the computer can walk on arbitrarily small slopes, and the smaller the slope, the slower it walks. Yes?
So does this basically work by like, it sort of bounces off the ground, off the slope source, like at one foot hits the ground, then the momentum gets transferred back into it?
Well, you can say all that. I mean, the way I would say is it works by satisfying the laws of mechanics which you're learning in this class. And if you want to have some intuition about what's what, the simplest intuition for lots of things is energy, because energy is a scalar quantity, and it's easy to keep track of. So one way of saying how it works is that energy is lost in collisions, and it's made up by the gravitational potential energy, and it's that balance which makes it work. Why does it balance? Why does it keep moving and all that? There's no simple qualitative explanation. What happens when a foot hits the ground is it keeps moving, yes. It slows down, but it keeps moving. Yes?
Does this only work for a particular downward slope?
That's the same question we had before, and I have the same answer. It works for a range of slopes. Probably this particular robot on the computer works between about 2 and 6 degrees, something like that, or 1 and 6 degrees. Okay, so now we'd like to understand collisions, not to do such a hard problem as this one. By the way, how hard is it? Say, if you wanted to do a computer simulation of this, how much work is it? I would say at the end of this class, if you're like an A student and you worked all summer, you could get a computer simulation of this working. It's a little bit of a challenge getting something this complicated going. The first time we did it on the computer, I had 2 different students do it. and they each did it a different way, and they came and they got different results. And I said, somebody's got a mistake. And so we met again the next week, and they both walked in the room and said, I found my mistake. So they compared again, and they didn't agree again. And we went away another week, and they both came back and said, I found my mistake. And so they each had about 6, 7 mistakes. It took several weeks before they both got the same machine to act the same way on the computer. Very error-prone process. Okay. So let me just start just right in with an example, because there's nothing in principle new about this. You know what to do. And I have a square box that I use for this demonstration, but my square box is in my lab, and I didn't bring my keys to my lab when I went up there. But let's say I take this box, imagine a square, and I drop it. And when I drop it, it bounces up a little bit. And I'd like to figure out how much it bounces up. It doesn't bounce up very much. And this is something like what that robot does in one step. So what we're going to do is we're going to take this process and break it down into steps, so to speak. Which is, first, this thing falls, hinged about this point, and let's assume it doesn't slip here, and it conserves energy until it gets to here. Then, let's assume that when this hits, that there's no force all along this length, and all the force is concentrated in this corner. That's a big assumption, and it has a huge effect on the answer, but it turns out, at least for this particular box, that seems reasonable. So there's a big force here, and it's a collisional force. We can model it as an impulse. We can just look at the net force with respect to time. So what happens is between this state and the next state is there's some jump in the velocity and angular velocities, which is consistent with this changing from hinged about this point to hinged about this point. And we have to look at balance of momentum, angular momentum in that process, and then we'll conserve energy again while this rides up to here. So if we want to figure out how high this lifts up, we have conservation of energy. We have this collision to analyze, which we're going to analyze by doing conservation of angular momentum about this point, or angular momentum balance about this point, where in this case we're actually going to use angular momentum and not its rate of change. And then we have conservation of energy back up again. So let me take this example and draw it out in stages. So we're going to start out with a square box. Then it's going to tip to some angle, some intermediate angle. Then it's going to be in this situation where it's just about to collide. Then it's going to be in this situation where it does collide. Then it's going to be rising up. And then it's going to be in its top position. So we have the sequence of states, which I'll call 1, 2, 3, 4, 5, 6. And what we have is this is going to be the initial condition. Then we're going to have falling. Then we're going to have just before collision. And I'll call this T minus. Then we're going to have the collision. Bang. Then we have just after. And we'll call this time T plus. And then we have the highest position in the end. And I see that I left out a one state in here in between, which is the state where it's rising again. So another picture here where it's rising. So we have three processes: falling, collision, and rising. And the basic way we're going to solve this problem is we're going to use simple conservation laws for each of those three phases. Now for the falling phase, we could try to write and solve differential equations, but we already know what those differential equations are. In the falling phase, this is just a pendulum, and the differential equations are nonlinear differential equations, and to solve them, we have to use either the computer or elliptic integrals. And that's same also true for the rising phase. It's the inverted pendulum or pendulum differential equations. So even though we can't solve those pendulum equations with pencil and paper, we can solve things about them. For example, the pendulum conserves energy. So what we're going to have is these three processes. We're going to have from 1 to 3, 1 to 2 to 3 is we have falling. And in this falling process, we're going to have conservation of energy. Then we have this 3 to 4 to 5, which is this collision. And in this collision, we have one giant force at that right-hand corner. And I'll draw the collisional free body diagram. And then we have the gravity force, but the gravity force you think of as being relatively small during that small interval of time when that collision force is large. So in this small interval of time, we have conservation of angular momentum about point C. And then we have the final steps, 5 to 6 to 7, where we have rising. And again, we have conservation of energy. So here what we're going to say is that E1 is equal to E3. And what do I mean? Which E do I mean? I mean the total energy, which is gravitational plus kinetic energy. Here we have that H with respect to C3 is going to be H with respect to C5. And here we have E total, and this is 5, is equal to E total 7. So to actually figure out how high this box lifts up, all we have to do is flesh out these quantities, these angular momentums and energy, in terms of, say, the angles and angular velocities of this block. Yes?
Where is point C?
Where is point C? Point C is always the point of interest. Here is point C. Other questions? Okay, so now let's flesh this out in terms of the variables. This system has 1 degree of freedom, so we can keep track of it with some angle and some angular rate. Let's pick a coordinate system, say, like this, with I and J. Implicit with that coordinate system, if we want things to work out with cross products and so on, is that angular velocity is going to be positive in the counterclockwise direction. Unfortunately, the way I set up this demo, I have it moving in the clockwise direction, so all of our angular velocities are going to be negative. And so, sorry about that. We can pick some sides for this thing. We can name a point in here G. We can say the mass of this thing is equal to m. We can say the moment of inertia is equal to something or other. What is the moment of inertia of, let's say, a uniform square plate? Anybody know? Anybody think they know? Okay, well, this is a calculation that you should be able to do by yourself. So do this. Make sure that this is something you can do. It's an exercise from TAM 202, sort of, from Math 192. It's in the book. I'm going to skip that unless you ask me to do that calculation. Okay. So let's look at 1 to 2 to 3. 1 to 2 to 3. This process and figure out what we have. 1 to 2 to 3. We're going to now try and do this thing in detail. What do we have is we have the kinetic energy plus the potential energy in state 1 is equal to the kinetic energy plus potential energy in state 3. We have the initial kinetic energy in state 1, which is equal to what?
0.
Good. You don't have to listen. You just say 0. And then we have plus the initial potential energy. So And then this is equal to the final kinetic energy plus the final potential energy. So we need to work out what these quantities are. Okay, now I've got a side story for you, totally irrelevant, but just got to throw it in here somewhere. How many people think this class is harder than TAM 2020? How many people think it's easier than TAM 2020? Most of you think it's harder. Now, I just learned last night that TAM 2020 is ranked number 7 in the nation for the hardest class of all colleges classes in the United States of America. TAM 2020 at Cornell. TAM 2020 at Cornell is the 7th hardest class in the country. Now, what does that make this class? At least 6, right? Do you want me to put a link on the webpage for that? So yeah. Okay. Yeah. Yes?
Well, to be fair, it was from the website per campus, and I really don't know how many of them are actually engineering students, so which is why I think engineering classes is probably not very highly represented on that.
You're saying you can't trust everything you read on the web? Is that? Okay, so what's the initial potential energy? If we take our datum for potential energy right here where the thing's on the ground, then initially we have this, the center of mass is up here some height. What is that height? It's L over 2. Well, what's this distance here? It's L over the square root of 2. So we have EP1 is equal to L over the square root of 2 mg. And then what's EP3? It's just L over 2 mg. And then what is EK3? What's the kinetic energy of this thing just before it hits? Well, one way of thinking about it is by using the moment of inertia about what point here? I've got to get this point a name. Here's point A. Here's point G. Here's point C, where it's going to hit later on. There's 2 ways to write this. One of this is 1/2 the moment of inertia about point A times omega 3 squared. Or another way to write this is as 1/2 the mass times the velocity of g at state 3 squared plus 1/2 ig times omega at state 3 squared. So it's 2 equivalent ways to write the kinetic energy of something which is rotating about some point A. One is to think about it as a rigid object with some moment of inertia about point A. And I do not advertise that you use this. This is the physics 112 way of thinking. And what's wrong with this is that it only works if you're rotating about some fixed point, which you are in this case. Another way is you can always write the kinetic energy as the kinetic energy of the center of mass plus the kinetic energy relative to the center of mass. And that's what the second term is. Okay, so we can use either of these 2 results. What's nicer about this one is we don't have to use the parallel axis theorem. This one we do have to use the parallel axis theorem. What does it say? It says IA equals IG plus L over the square root of 2 quantity squared times the mass. In this one we don't have to do that calculation, but instead we have to calculate these various velocities. Let me use the second version of this. So what is the velocity of this point G just before that collision? Well, it's the angular velocity times the distance of the point G from the point A, quantity squared. So this thing here is the magnitude of the velocity of G just before the collision, and that's in step 3. And then we have plus IG, and then we have our omega. This is what omega is. This is omega 3 quantity squared with a 1/2. Okay, so we can write this whole thing then as a formula from which we can calculate omega 3. What's that formula look like? We take our energy before equals our energy after. Our energy before now is L over the square root of 2 mg equals our energy after, which is L over 2 mg. So the potential energy is a little less, and that's made up for by this kinetic energy, which is this omega 3, quantity omega 3 squared, multiplied by some big stuff here. And what is that stuff? It's a half of, and then we've got two terms. We've got m L over the square root of 2 squared, m L over the square root of 2, quantity squared, plus Ig. So this turns out to be just what we would have got from the parallel axis theorem. From this, we get that omega 3 is equal to something, which I'm not going to calculate. Some mess. So by using conservation of energy, we can figure out what is the angular velocity of this just before it hits. So I didn't do the final bit of algebra, but that's something we could calculate. Any questions about that? Yeah?
Why is it, again, that you can assume that the force is at that point?
Why is it that when I get to the collision, which I haven't got to yet, the part that I'm about to do, why do I assume that the force is right at this corner point? Because the box is kind of indented and the part in between doesn't actually touch.
But if that weren't true, then this would not be true, right?
Well, everything so far is okay. You're talking about the next calculation I'm going to do. The next calculation I'm going to do assumes that there's no forces along here. And it strongly depends on that assumption, and you get a totally different answer if you don't have that assumption. So in book problems of this type, they will draw a box that has a little bump at these corners to make it clear that there's no contact in between. Okay, so that is the this 1 to 2 to 3. Now we want to do the new part today, which is 3 to 4 to 5. And so we start out with this collisional free body diagram. And the collisional free body diagram looks like this. We have this big force. And then we've got this teeny little mg force, which we neglect. So this big force, bang. And I'll call this P, or I can think of it as a big force, or I can think of it as an impulse. And for this purposes now, I'm going to think of it as an impulse. So what we'd like to do is we take angular momentum balance, and there's two ways we can do this. We can jump to the impulse equations, or we can derive the impulse equation from the angular momentum balance equation. If we start out by saying the sum of moments relative to c is equal to h dot relative to c, and we take the integral of both of these dt, what we get is that the angular impulse relative to c that's what this quantity is, the integral of moment, that's an integral there. And this is from t minus to t plus, integrating from t minus to t plus, is equal to the change in the angular momentum relative to c. So if we look at the integral t plus, that says the integral of the derivative of something, it just tells you how much that thing changes. The integral of the velocity, like the integral of the rate of change of position, is the change in position. The integral of rate of change of angular momentum is the change in angular momentum. So we have either we start with the derivative form and integrate, or we have the impulse form. Some people would just call this balance of angular momentum because we actually have angular momentum over here. But what goes on the left side is angular impulse, not torque. Anyhow, what is in this free body diagram the angular impulse of all the forces relative to point C? It is 0. So here we are at point C. And all the forces that are significant pass through this point. This puny little gravity force is not so important, right? If I happen to put my finger underneath this, ow, that hurts more than holding this up, right? The force is much bigger, ow, than this one. And so that gravity force is negligible. So this thing is 0. So that tells us that delta H with respect to C is equal to 0. So what we say then is that H with respect to C in state 5 is equal to H with respect to C in state 3. That's what I said at the beginning when we laid out the problem. Step 2 of this problem, we do balance of angular momentum about point C. Now we get to the hard part of this problem, which is doing this calculation. So this next step is actually the only challenging part of this question. Perhaps organizing your thoughts to think of it as, oh, there's energy conservation, then there's angular momentum conservation, then there's energy conservation. That takes a little bit of insight. But in terms of technical skills, the only thing that's hard is this next step. So now I'm going to erase the blackboard, and then I'm going to move that back down again, because I didn't need to do that. And I think I can skip this now. Okay, any questions before I go on here? About the layout of the question or what I'm doing? Okay, so this is now the hard part of this question. The hard part is evaluating this thing here. So on the left-hand side, we have to calculate, let me put 3 and 5 here, just so I have before and after, left and right. And that was actually 3 and 5, right? So on the left-hand side, I have to calculate the angular momentum relative to point C before the collision. And on the right-hand side, I have to calculate the angular momentum relative to point C after the collision. What's the deal here is that before the collision, I'm calculating angular momentum balance relative to this point down here. Just before the collision, I have a motion of the center of mass in that direction, plus this rotation. Just after the collision, I have a motion of the center of mass in that direction, plus the rotation. So both times we're rotating about points, but in one case we're rotating about a point which is different from the one we're using for angular momentum balance. In the other case we're rotating about a point which is the same as. So in this before collision calculation, I cannot use, for example, the moment of inertia about point A or point C. In the second calculation I could if I wanted to. But in the first one, I have to say the angular momentum of this system about this point is made up of 2 parts. One part is the translation of the center of mass, and the other is the rotation about the center of mass. And that translation term doesn't have a very big effect relative to point C. In fact, how big is it? Exactly. Okay, so we'll see that. Okay, so we're going to look at this box. In all cases, it's going to be in this configuration. In all cases, we're going to look at this point C, and we're going to look at this point G. So beforehand, when we look at the angular momentum relative to point C, we have the velocity of G, and this is the velocity of G in state 3. These superscripts are not powers. We have the position of G with respect to C crossed with the velocity of G in state 3 multiplied by the mass plus I G omega 3, and this is in the k direction, and this is before the collision. And after the collision, we have exactly the same terms, but we have a different velocity here. So we have r of g with respect to c crossed vg in state 5 plus I g omega in state 5 k. Okay, now if we're going to assume that this thing is a square, we can calculate this velocity before the collision as the velocity of a point which is rotating about point A. So this velocity here we can put as a position is omega 3 k crossed with the position of g with respect to A. And this is an A here and not a C. So before the collision, this thing has a velocity which is rotation about this point. Then we're going to take the cross product of that with the position of g with respect to c. Now if this is a square, this velocity of g before the collision, so here's the velocity of g in state 3, is along the line from g to c. Therefore, this cross product is going to give us 0. We can work it all out with i's and j's and so on, and we'll get 0, but we can see from the picture that it has to give 0. Any questions about that? Anybody want me to repeat it? Okay, so before the collision, the angular momentum of this system relative to this point is 1 due to motion of this point g, and 1 due to rotation of this box. The motion of point g before the collision is a rotation about point A. So the velocity is given by omega cross r. Or, just looking at the picture, we know this is going in circles, it's going in that direction. If this is a square, that direction is pointed right at point C. So then when we look at the angular momentum of this object due to translation, we get this position vector crossed with this velocity. It makes no contribution. The center of mass of the system is moving directly towards this point. Therefore, there's no contribution from translation to angular momentum of the system beforehand. So this whole thing gives 0. And as I said, if you don't like that geometric reasoning, you can carry out all these cross products and you'll get 0. Afterwards, we have this Vg of 5 here. What is this thing? This is something which is pointed in what direction? It's pointed in that direction. And its magnitude is what? It's omega 5 times this distance. And here we have this distance again. So we have, and then we get the direction of this thing is in the k direction. Actually, it's the minus k direction because we have omega 5 is positive this direction. So this whole quantity here turns into omega 5, that's omega in state 5, multiplied by L over the square root of 2 squared. I've left out a mass here, multiplied by the mass. And then here we get a second term just like the first. So now let's see if we can get all these terms here. Remember that we know omega 3 from the previous calculation. So we have Ig omega 3, that's omega just before the collision. And this is multiplied by k. So we're going to take that whole expression there, and we're going to take the dot product of both sides with k. This quantity is going to be a negative quantity because before the collision omega 3 is negative. Then on the right-hand side, we have this L over the square root of 2, quantity squared, multiplied by the mass, multiplied by omega 3, and that was also, that was in the plus direction, I think is the way that worked out. That's in the plus direction if omega 5 is positive.
Is that omega 5 or omega 3?
It's an omega 5 here. And then we have plus Ig omega 5. So given omega 3, which we have, because we found that from conservation of energy in the first step, this then tells us what is omega 5. And what are we going to find? We're going to find an omega 5 less than 0 because this omega 3 was less than 0. It was a bad choice to use superscripts because it confuses with power. So I wish I'd used subscripts, but never mind. Okay, give me 30 seconds more. Sorry. Now that we know omega 5, we can use conservation of energy to figure out how high the thing lifts up when it goes up the other side. And it goes up a surprisingly small amount, only about 1 or 2 degrees. Okay, that's all. Sorry I kept you late.